Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is, well, this is going to be probably the first of a two or maybe three-part series on describing motion in the plane. So what we're looking at here, we have some sort of track or path that this particle can follow. So imagine in this example that this particle is moving along this path and in the following direction, and not necessarily a constant speed. So this particle's position and velocity could be changing. Now, the first thing to realize about this is that there's multiple or several sets of coordinates we can use to track the motion of this particle. Right. This particle at this instant has a position vector, which I'm going to call R. And this position vector could be expressed in either XY coordinates, which will be the main focus of this video, or conceivably it can also be expressed as a distance and an angle, which will be what are called polar coordinates. So for this video we're going to focus on the Cartesian formulation here of describing the motion of this particle. So the position vector has an x component, which would be like this if I drew it, and a y component. And we can express the position of this particle as the x component in the I direction and the y component in the j direction. Now, in a standard Cartesian coordinate system, we would normally just call this x and this y. So I'm going to go ahead and redraw this position vector as xi plus yj. Now, the position vector tells us where it's at. The velocity, right, is the rate that position changes, so it can be expressed as dr dt. If we go through and time differentiate this, we're going to get that the velocity vector can be expressed as x dot I plus y dot j, where again the dot notation is just shorthand for time derivatives. So I'm going to write this off to the right. So dx dt, again in shorthand, would be x dot. dy dt and y dot are the same thing. Now, oops, and this is a unit vector here. One thing I'd like to point out is that in this example, I and j are not changing in direction. And when this has been differentiated, I've inherently used that fact, because if I and j were actually changing in direction, they would have time derivatives as well. In general, you have to product rule this, and you have to product rule this. But again, in this example, I and j are fixed. We'll see later on in the course, we'll see examples where I and j will be changing in direction, and you have to get used to looking for that when you're differentiating functions. All right. So the next step here to tell us about the acceleration, well, acceleration is the rate that velocity changes. So in the language of vectors, that would be dv dt. And if I go through and differentiate this, this is going to give me x double dot I. Again, keeping in mind that I is not changing. That's why we're not product ruling this. And y double dot j. So here's expressions for position, velocity, and acceleration that would describe this particle as it moves through space along this path. Now, in this picture, if I were to draw the velocity vector, I'm going to do that in blue. Velocity vectors are always tangent to the curve. They have to be. There's just no possible way it's not. So at this instant in time, the velocity vector, whoops, that doesn't look tangent. The velocity vector of this particle might be pointed something like this. Okay. The acceleration vectors, however, do not need to be tangent to the curve. And in fact, in most cases in plane motion, they won't. And I'm going to draw the acceleration vectors in red. So if you've had a semester of physics, hopefully you're familiar with the idea that acceleration comes in two different flavors typically in physics. You have what's called tangential acceleration, which has to do with changes in speed. In this example, the tangential acceleration would describe how fast the magnitude of this velocity vector is changing. Then you have what are called centripetal accelerations, and centripetal accelerations have to do with changes in direction. In general, centripetal didn't want to do that. In general, centripetal accelerations are calculated by v squared over the radius of curvature, and they're always directed towards the center of curvature. In my example, along this path, the center of curvature is maybe about here. This line would actually make a right angle to the path for finding the center of curvature. And again, in this example, it's very important to realize the center of curvature along this path at this point is not the origin. If this were a circular path around the origin, right, then this is where the center of curvature would be. But in general, the center of curvature does not have to be at the center of your coordinates. It's the center of curvature of this path, like right in this region here. So in my picture, that would be roughly here. So if this particle were speeding up at the instant shown, the tangential acceleration vector would point this way, parallel to the velocity vector. If this particle were slowing down, the tangential acceleration vector would point this way. So in general, when the particle is speeding up, the tangential acceleration vector is in the same direction as the velocity, and when the particle is slowing down, the tangential acceleration is in the opposite direction. Now, for the sake of this example, I'm going to go back to assuming it's speeding up. Okay. Now, the centripetal acceleration vector in this example would point towards the center of curvature, which would be maybe this way. So there's the centripetal. The net acceleration vector is the vector sum of the tangential and the centripetal accelerations. So if I were to draw that in this picture, and what you have to imagine is like picking this vector up and plopping it right to the end here, or picking this vector up and plopping it right to the end here. In either case, you would end up about right there, give or take. So in this example, and this is the important vector, that's the net acceleration vector at the instant shown. So in this picture, the two most important vectors to pay attention to right now are this one, the velocity vector, and this one, the net acceleration vector. Now, you'll notice that they do not, in this example here, they are not in the same direction. As this particle moves along this path, maybe if I pick another spot like right here, right at that instant, right there. The velocity vector, and I'll go ahead and draw that in blue, again, tangent to the curve. Whoops, that's not quite tangent. Maybe something like this. Now, the reason I drew this velocity vector longer than the first one is because I've assumed in this example this object is speeding up. And then the acceleration vector, I'm going to try to draw it without drawing the components. The acceleration vector would have a tangential component this way in the direction of the velocity, a centripetal component this way. So the net acceleration vector might point, in red, might point something like this. And again, I'm going to save like how are these calculated. I'm going to save that for another example. So the purpose of this video is just meant to be kind of an introduction to motion in the plane. Some important points are, well, one, knowing how to express a position vector in Cartesian format. And in the next video, I'll talk about how to express that vector in polar coordinates. Two, how to take that vector and use it to calculate a velocity vector, and that's just by differentiation, time differentiation. In the examples I'm going to do in the next video or two, these will be constant in direction, but they do not have to be. There will be cases later on where those things will be changing in direction, and hence we'll have time derivatives. So when we differentiate this function, reasonably easily, this is what we get. And then we can get the acceleration vector, again, by differentiating these terms, and again, time differentiating these terms. Another important part of this video is understanding the graphical relationship between the velocity vector and the acceleration vector. That's a really important fundamental in dynamics as a rule of thumb, is understanding acceleration directions, because acceleration is a key concept for Newton's second law equations. So Again, in this motion along the path, velocity vectors are always tangent to the curve. But acceleration vectors do not have to be, because you have these potentially centripetal terms that give you components that make a right angle to the path. The centripetal accelerations are always point towards the center of curvature, which will give you at least conceptually an idea of where they point in any given problem. And there's other types of accelerations that we'll be exploring later on in the course. Particularly, there's what's called a Coriolis acceleration that has to do with effects that are not happening now, so I'll save that for another time. But anyway, this video is just meant to be kind of an introduction to motion in the plane. I hope that it successfully does that. Have a great day.